Resume recording. One second, let's try. Okay. Let's see if it will work this time. Well, welcome to our one of the next lectures in the course number whatever. If you are in the graduate school, it is 676. If you are in undergraduate program, it is 476. But number of credits is the same. And if you are in the undergraduate school, the grading would be much more rigorous. Just to make it fair, because of like difference in 200. I admit that I was scaring you, and I was scaring myself with an announcement that we will make presentations today. If you have prepared them, it's good for you, but we will not make them today. I have sent an announcement about half an hour ago, and I was announced it in last night, so that your presentations are postponed by 1 week. Please use your time wisely and use me as a resource. You can prepare it like now, today, in a day, and send it to me so that we cooperatively improve them, and then you feel less stress in the last time. When it will be Wednesday night before the presentations on Thursday, I do not want to be this way, but I will become very nervous. I will start sending private emails, calling, telling where is your PowerPoint transparency if you do not send it ahead of time. So be prepared for that, and if you make it ahead of time, then everything will go smoothly. Also, you do have examples from previous years. If you do not care about anything, you can just find the one you like, copy paste, and present works of someone else. If you carry either high moral standards or you want to learn more, you better prepare your own slide. Just looking on the slides from others as a guide. The idea is that you show your practice, you show your personal experience, especially the history of success and failure. Because something works, something doesn't work. Maybe the actual building of atomic models can be super simple, but going through the Linux is much more complicated. And you may share this with the rest of the class. I'm not pointing at anyone personally. It is challenging for me. What are we doing today? We need a little refresher, like who we are and what we are doing. And we are in the class of computational chemistry. We want to model the properties of materials and molecules by running right codes, and we are picking up a little of background of these codes. For a long time, we were exhausting our young, and maybe not young, brains for separating degrees of freedom, electronic and nuclear degrees of freedom, because we want to live an easy life, and we want our computers to live an easy life, to have as less degrees of freedom as possible. And we were successful in separating electronic and nuclear degrees of freedom. Now we are forgetting about electronic degrees of freedom for a couple of lectures and dealing with nuclear degrees of freedom only. The nuclear degrees of freedom are positions of ions that you were clicking and drawing yesterday if you were not missing yesterday. The codes that we use help human hand to find optimal interatomic distances. And it is a task one for any computational chemistry research, and we are going to go into details how this optimization is going. If everything goes as planned, which sometimes doesn't go this way. We will pretend that we are computers today and solve a simple optimization problem by hand. Okay, let me practice this too. Content sharing. Test 1 1. I'm checking if there is a recording. I don't know if it will be on recorded. I don't know if I'm pushing the right buttons. There are too many of those. But maybe by the end of the course, I will pick it up. Do you see my mouse? Do I see my mouse? Where's the point? Okay. Do not look on this date. It will be different. Do not look on this date. We are meeting in the different room. I was able just to update the number of the code of the course. So when we met last time, we did agree that for any degree of freedom, for any Cartesian projection, there are two equations. One for position of ions, another is for position of ion, another for momentum. And this comes from Born-Oppenheimer separation, and we are in the classical path approximation. So we are dealing only with positions of ions and forget about the width of the nuclear wave packet. We just aware that it does exist. In some exotic problems, one needs to take care of it, but today, no. Today we are happy without it. And there are two ways to take care of width. One is do quantized nuclear wave packet, and another is just make a swirl. I don't know how to pronounce this word. Swirl, multiple trajectories of the same system that diverge by initial conditions a little bit, and then one goes one way, another way, and it will represent a little uncertainty of the position. So it's like mimicking quantum distribution with multiple quantum trajectories. Okay, we are dealing with these equations. So the reason to change position is velocity. No one objects. The reason to change velocity or momentum is force. Like if a projectile runs in a free space, it will run in free space until it hits the planet or whatever, or another object that will apply force to it. What is the force mathematically?
Would it be potential energy surface?
Huh?
Potential energy surface?
Okay, suppose you do, huh?
Gradient?
Yes. So if I would be able to write on the screen, I would write the word gradient. But I can just mimic that I do. So we need a gradient of potential energy surface. Here should be derivative over R. And it gives us the change of the momentum. It's just boring to go across pre-recorded slides, and I just want to scratch something quickly. And we can go from two equations to one. So if we apply dt to the first equation, we get d2 r dt squared equals dp dt, but we know that dp dt can be replaced by the this derivative. I hope I haven't made a mistake in this simple one-step derivation. If you find, please let me know. So what do we get? What is the name of this equation? Second derivative of position can be called good. Objections? No. Letter A. So then we multiply both parts by mass, and A equals, and according to Levi, the gradient of the potential energy surface can be referred to as force. Any bells clicking, whooping on this equation? Right? So how do you verbalize it? Acceleration gained by something is proportional to force applied to this something. Good. Camera facing class. Content control. Enable content sharing. Okay. That's hard. So plugging in, getting the equation. And we are very close to numerical solution of this equation. So we do have a black box or a good wizard that will always provide u as function of r by request, as in the fog of war. We can make it bright at any specific spot, but we cannot do it everywhere. And we need to use this resource in order to find such position where there is a minimum of potential energy surface. So we need an algorithm to go to the minimum. I'm going very slow in very primitive things so that we all are on the same page. If we jump high, it could be least pleasant. So we stop being mathematicians now, even if you never were mathematicians. We will be programmers who design algorithms and encode them into programs. And for the programmers, for numerical scientific programming, we do not have such thing as function or derivative. We do have just set of numbers. Everything is represented in form of discrete set of numbers. Same as your experimental spectra in Excel. Just set of points. Even if you connect them by a line and they look continuously, it is just set of discrete numbers. X and Y. So we need to recast this equation that we had also in a numerical form, which means that we will have discrete positions in space, discrete values of potential energy, and discrete values of time if we use time in this calculation. So everything is discrete. Discrete position, discrete momentum, discrete force, discrete potential. I am going to the blackboard and I'm going to reproduce what is written here because I feel bored looking at it. I don't know about you. maybe you do not enjoy it either. It would be more vivid if I would scratch it directly on the screen, but if you have a blackboard, for so instead of R, we will have set of positions R1, R2, R3. Then at each point you will have different value of U of R. U1, U2, U3, U. Then how do we define force? du dr. What is the definition of derivative or gradient? It could be, let me enjoy myself as a screen. So what is the derivative? It could be first lecture in calculus, if you remember it, or maybe second.
Change in y over change in x.
So instead of d, you write delta u over delta r, right? And if you are looking for local derivative in the vicinity of these 2 points, how do we recast it?
Final minus initial.
Huh?
Final.
It's too sophisticated. Here is first u2 minus u1 divided by r2 minus r1. And this, of course, there should be a limit. In the limit of delta r goes to 0. Right? Limit delta r goes to 0. Okay, so here, if we want to set up a column for derivative, we will just always compute u n plus 1 minus u n divided by r n plus 1 minus r n. Now the sophisticated form as Levi suggested. Final minus initial. What else do we have here? We have derivative over time. So we need to use time, even if we are not, if we are optimizing, we do not care about time. We need just one minimum forever. But as an artificial method, we can use artificial time just to find it. How would you solve it if you are a mathematician? Before we go to numerical. Differential equations are solved by integration. And if we do, you want to solve it? It would be a great help.
E to the power something.
We do not care about.
Wouldn't we want to separate variables?
No, much simpler.
Oh, okay.
So let's solve it with limitation. Solve for infinitesimal increment of time. Suppose we know position at time t equals 0. And we do want to know position at time plus delta t. 0 plus delta t. It will be equal r of times 0 plus something. And this something depends on delta t. I'm 100% sure that if we make a little exam, this question, how to answer this equation, everyone is able.
Can you say it or something?
Yes, that's correct. So what should we do, suppose that we do know the momentum and we know the acceleration. It is middle school science. We don't need to go to university to answer
Can you
this.
just do acceleration times time?
Right? If my speedometer shows that I'm 100 miles per hour, then each hour I will be 100 miles forward. Let's see. If my engine is stalled and there is a front wind, I will feel friction, like friction force, acceleration that will stop me. So it is a revision of middle school science. And instead of A, we can put what? We can put minus d u d r divided by m, right? Objections? No objections. Either I'm correct or you didn't find my mistakes. Why? Because if we integrate left and right part, it is just what happens. You want to practice?
No.
I have a senior colleague whom I was seeing teaching a class, and I've learned an excellent way to sound logical. It has no, the following sentence has no connection with actual logic, but it sounds very convincing. You need to open your eyes wide and see. Like, quantum dots blink because it is what they do. It was the same logic. Like, integration gives you this answer. But what are the practical benefits for our goals? If we do have some complicated potential energy surface, could be multidimensional, but in our case it is one-dimensional, we are staying in a specific point, U of R. We know R1, we know U1, and you have trial increment R2. So based on these 2 points, U1, U2, we can compute acceleration. And then if we agree of what we take as the delta t, we can predict and maybe assume that P will be equal 0 for simplicity. We can predict where the system wants to go. And we can move the system in the direction it wants to go. Move it forward. Probably it will be somewhere in this direction, if it is this potential. Then we can use these 2 points to recompute force and go further. And then, if you go further according to this algorithm, we can go in the direction opposite to the slope of the surface, and then it needs to turn around, right? So our goal is to write down an algorithm that will help our little explorer to reach the minimum, with an assumption that we can go on the very small steps. Well, if you take bigger steps, it will just explode. It will immediately go like to the bigger distance and to dissociation. Okay.
A question.
Please.
After the first step, are we still saying that momentum is 0 for all time?
After,
So,
repeat.
so once we do the first guess step, so we have our initial geometry, we do our guess, and you said that p is equal to 0.
Mhm.
Are we saying p is equal to 0 the entire optimization, or after the first guess are we incorporating p back in?
We can do two ways. We can set up with p equals 0 all the time, or we can accumulate momentum but introduce damping.
Okay.
So it will be not optimization but simulated damped relaxation. Yes. Content control. Okay, so here are the boring stuff that everyone is happy with our discussion. Good. So it is what we talked about. So the force in finite differences, and here is how we solve the equation of motion in finite differences. So we can set up here before everything was correct. Now there is a little trick which partially addresses the question of Levi. We can neglect momentum at each step, but assume that there is a instantaneous damping that prevents our system to propagate in the direction of the force. So the force is so strong that it will draw us to the wall, and there is a little damping force that prevents us from going so quick. So it is just a measure to avoid this desorption, breaking the bond too early. So we just make an artificial like factor, 0.1 or 0.5, so it goes not as vivid as it could be. Now I have to admit that Seth was looking far forward in the future by asking question about local minima. They do exist, and it is an objective problem that right now we are not going to address. We are going to it is called scientific approximation. We are going to discuss how to reach one local minimum, hopefully a global one. But for going into jumping into several, one needs additional steps. So if we are already in the vicinity of a minimum, then potential energy surface with a good approximation can be assumed as a harmonic. We do not need to do it all the time, but it is a good approximation for learning. So, but in real life, it could be much more complicated, and in addition to minima, it may have saddle points and several minima. If I will be a programmer who has zero knowledge about science, and I will get an assignment, write a code that will find optimal geometry. I would write a code in 4 lines, or maybe 10 lines. First, make a cycle over all possible interatomic distances for all ions. Compute value of potential energy surface and record it into the array. Okay? And then make another cycle to go over all points in the array and sort them according to in ascension order, or find the minimum. Then report the position that was given this minimum. Would be absolutely correct, but absolutely impractical. Because why?
There's an infinite number of points.
Right. Large number approaching infinity. So suppose that we have our one Cartesian coordinate, 1 degree of freedom, and we represent it as set of discrete points. Suppose we are not picky for high precision. We will be splitting on just 10 grid points, which is not very many, but 10 grid points per degree of freedom. Then for diatomic, just 10 points, which one can indeed compute and order. If we do have 3 atomic, I think next year it can be formulated as a little quiz. Compute number of degrees of freedom. 3n minus 6. So for 3 atomics, how many degrees of freedom?
3.
3? I believe you. It means if we have 10 grid points for each degree of freedom, then total it will be 1,000 grid points for water molecule that we have to scan. If we do have acetylene with 4 atoms, how many degrees of freedom? 3n minus 6, huh?
It's minus 5. It's a linear molecule.
Okay. Linear?
Acetylene's linear.
Yeah.
Yep.
Yeah, so it's
so it's
minus
3 and minus
5.
5.
Oh,
Yes,
because it cannot twist.
Yes, triple.
So how many degrees of freedom?
Chase.
So
7?
7. Yeah.
Ah, it's even worse than so there's 10 millions point, which is fine for our modern PC and maybe Excel. Make an ordering of 10 million points yet possible. But if we want alcohol, even not the drinkable one, but the methanol, yeah, it is getting to the limit of gigabytes and hours, and as long as we expand, just the number of grid points becomes too big. So in this space of many points in this multi-dimensional space, instead of looking on all of them, we need to find a path that will bring us as close to the minimum as possible, which is relatively simple if we are in the vicinity of the minimum. If we are apart, there will be additional tricks. But let's start from something simple. I agree with what is written. So we try to live an easy life and minimize our effort. Okay. So if you didn't catch me lying, or if you didn't, if you agree with everything what was Reno said about this gamma parameter, then we can set up an algorithm. How do we compute the change of the position? So we need to couple of points with potential energy surface. We need the energy difference between these 2 points on potential energy surface. We need to compute the gradient, and then we plug in this gradient into the expression for delta R, for change in position, with 2 parameters. One parameter is artificial time step, which we can make something like femtosecond or attosecond, whatever. Or if we do dimensionless, we can set it just 1, if you do some mathematical experiment. And then we need this damping parameter, so that we have a prevention from going too far into dissociation limit. And as soon as we do this operation, we make 1 step. Then we need to go over and repeat. Here is my favorite part of any class. We do 1 step, then another step, then third step, then 10th step, then million step. When do we stop? How do we know that we reached the minimum? And yes, we will come to this. Why we are asking this question? Because if we are in the algorithmic type of thinking, we are in the danger. So I don't remember if I told this joke in this audience, but I like it very much. It is very appropriate. Some of you may have heard it already. Maybe from you, maybe from someone else. So there was a big company, hired a talented programmer, and suddenly he didn't came to the work. People started worrying, waited a day, 2, 3, then they sent someone to his apartment and found this programmer like sitting complete, still alive, very blue, in the bathtub with the shampoo in the hand and shaking and they, what are you doing here? Just pointed out on the algorithm. Apply to the head, wash out, repeat. So we need to set up some breaker, some tolerance limit when to stop this algorithm. What is shown here? Huh? Any ideas how we call this ugly images?
Like for flowcharts?
Yes, yes. So we are going to play tinker toy of making these blocks for flowcharts and make an algorithm out of them. And what we have for one step is just a subsequent set of math operations. And the arrow means just flow of logic, flow of data in the right direction. But we need to make a loop and we need to make a breaker. So we need some point where we can go either one or another way. So some condition. And the condition is what Levi told tolerance limit. So we can, for example, we can tell that if the change of potential energy is really small, if delta U final minus U initial, is less than some small number, and this small number will be a parameter. Make sense? I just want to avoid boring indication of what is written on the blackboard and showed here. So we start with our gamma initial position. What else? Choice of delta t and the tolerance limit. And then we are going to compute delta U, delta R, gradient, and increment of the R equals Rn plus 1, Rn plus delta R. And then the thing that we just mentioned, we need to compare the new value of energy, potential energy computed N equals U of Rn plus 1. So we need to compute how the new value of energy differs from old value of energy. And if they are less than some small number that we define originally at the beginning, if it is yes, then it is success. We just draw a big star on a screen and play music and say, mission complete. Or we can print or whatever, save into file the value of r n plus 1 and u n plus 1, which will be our optimal geometry. Here we do it only for 1 degree of freedom, but it will be answered. The position on the potential energy surface that corresponds to minimum of energy. If it is no, then we redefine un equals u n plus 1, rn equals rn plus 1, and repeat the whole cycle. And then we program it, loop it, and sell it to chemists and charge them. Or if we are already chemists, then we just write this code ourselves and pay to no one. And control. Okay, I don't know if it was on record. So for this diamond, the good word is branching. So we do have flowchart for the algorithm of geometry optimization. Also, if you write it for voiceless computer, we can give hard tasks to computer. We do not care. But if you imagine that we will follow this algorithm ourselves, we should make it really simple. We cannot do it too many times. So, if you want it to be proof of concept doable by human being, we may add another check. If n is less than 10, or maybe less than 5, then continue. If n is bigger than 10, then we stop everything and report failure, telling that initial geometry was wrong, or potential was wrong, or delta t was wrong, because sometimes we still can get into the position of a programmer in a bathtub. So if it is too long, you can stop. Okay. So if you do not like the scratching shown on the board, here is a little more elegant scratching on the screen. So the algorithm is with a couple of branchings and just computing if delta U is smaller than tolerance epsilon, then we report success. If it goes too long, then we stop it. Any objections or questions right now? The optimization itself is not as critical and super important. We will do much more pleasant and interesting things. But the general way how the algorithms are set up are going very similar to this idea. And these simple ideas of optimization cycle and reaching tolerance limit will be repeated in several other methods for electronic structure too. So we better learn on simple examples and then just grow slowly but surely. Okay. How can we check if we are doing the right thing? We should do an example. And the simplest potential is just r squared without any coefficients. with predominantly known minimum of r equals 0. But if the algorithm is correct, we can start somewhere apart from equilibrium, run the algorithm, and try to reach the minimum. So we can set up initial position. We can set up the tolerance limit. We can set up initial increment because we need 2 points to compute the gradient, right? And we can set up delta t. I've made it up as square root of 2 because we still need to make square of t, and it will be easier to compute. And gamma is 0.3. What are we doing now? We are taking these little pieces of blank paper and trying to pretend that we are computers. So, debugging of the algorithm, checking whether the computer will sustain this task or burn. How do I make it a fair game? It would be unfair if you do it and I don't. I probably can make this table on the blackboard and run between the board and the computer. I know from experience that you will do it maybe 5 times quicker than I. But please go forward.
What was the delta R again?
Delta R initial
Yeah.
1. Step. Equals minus m d delta t squared over 2. And we set up mass equals 1 so that we do not spend too much of mental effort. So suppose that we have a such system of units where mass is equal 1, or we have a particle where mass 1. So initial position -5, u of -5 will be 25 because our potential is u equals r squared. Step 1, -4, because we do have our first initial step. At the step at the position -4, energy will be 4 squared will be 16, right? Delta U will be final minus initial. 16 minus 25 will be what? -9. Okay.
the force will be -9 divided by -1 with minus sign in front. Also -9, right? Okay. Delta T.
Wait, why is delta R -1?
You said plus one.
Okay, plus. And then it is plus. Good. Delta T, thank you for catching it. Delta T is square root of 2. Delta T square will be 2. Divided by 2 will be equal 1. Just to make our life easier. Now, we need to plug everything together. So, gamma, we agreed to 0.3. Delta U 9 times 1. What? So 9 times 3 will be 27. And divided by 2.7. What does it mean? That our new position will be -4 plus 2.7, right? Plus 2.7. I fear of arithmetic. Minus 1.3, right?
Now it's gonna get dirty.
Okay, you do the rest. I'm tired. Let's see what we have on screen. -9 plus 1. Okay, let's make our life easier so that we will spend time on arithmetic. Let's assume that this gamma equals 1/3. -1. Okay, then we can go quicker. So -1 squared will be 1. So final minus initial 1 minus 16 will be -15. Delta U is -15. And delta R was what? 3? 3. So we get -5.
But then we get the negative, so it's 5.
There's a minus in front.
Yeah, there's a minus in front of that. Yeah.
Okay, thank you. I do not want to be a computer.
I would rather have a computer do this.
Huh?
A computer can do this very efficiently.
Yes. But then we can lose track of what is going on. We do it a couple of times and then appreciate the help of our electronic friends.
Oh yeah.
I will.
You know, when there was an effort on building like nuclear reactors, atomic bombs, and the missiles, the computers were not as much developed, and there are historical records how the computations were done. So one hires like 100 calculators. Calculators mean person who needs to compute. They are given abacus, tables, and an algorithm, and they sit in the room and pass data between each other.
Slide rules.
So it was computational science of 40s and 50s.
No, thank you. One.
So, 1, yes, very good. So what do we do? Minus 1/3. Oh, no, this minus comes here into this gradient. 5 times 1, that's it?
Yeah.
5/3.
We should just say that's half.
Yep. Yep.
I'm close to it. So if we do not do cheating, then minus 1 plus 5/3 will be what?
2/3.
2/3. You see the significance of what we do. We observe our silly algorithm going 1, 2, 3. So going over the minimum. And if the algorithm is designed in the right way, it should jump back on the next step. 2/3. What is 2/3 squared? 4 divided by 9. 1/2 would be easier. Okay.
Round.
Delta U. Yeah, we should round up as much as possible. Final minus initial. 4 nines minus what?
1.
1?
Yeah.
Okay. Minus 9 ninths. Minus 5 ninths. Delta U by delta R minus minus 5 ninths. Divide, what was delta R? This one? 5/3? Not as bad. So we can cancel 5.
Then cancel the 3 to get 3.
Yeah.
Is it plus or minus 3?
Plus.
Plus? Are you sure?
Yes.
There's 2 negatives.
Actually, 1/3.
No, let's check.
Oh yeah, it should be 1/3
Yeah.
because you have.
You have to improve.
1/3.
Yep.
Plus or minus?
It's plus.
Plus.
You're positive.
Yes.
Yes.
Absolutely.
The number's positive too.
Not sure what the absolute value is on it.
Okay, square root of 2, 1, 1/3. Here,
1/3
third, times 1.
times -1.
Why -1?
There's a negative in front of gamma.
But we included it into
Yeah,
here.
that's already part of there.
Oh.
That's part of the delta U over delta return.
Oh, gotcha.
That's right.
1/9. Either I'm making error here or something is wrong with algorithm. I will check my notes. Because here we keep an increment into the wrong direction. Not good. Oh, let's follow the bitter truth. Step 4, so it was 2/3 plus 1/9. So it will be 7 over 9.
Apparently I can't do math.
U will be what?
49 over 81.
Be 10 over.
81.
No. Too much. And previous one, 4 over 9.
36 over 81.
Yes. 36. So this
So
is
that's
about
over-
13?
Yeah.
I can't believe I was doing this arithmetic while preparing. There should be some cheating to simplify the life. Let's check.
Maybe you did it on a computer.
No. Minus 15. Okay. 5. Yes. Oh, wait.
That's the same.
Yeah, that's the same.
Yeah.
Uh-huh. So it's 2/3.
That's why we're.
Okay. 2/3 like 0.66. Okay, I got to. Aha! Here probably I went away from this natural fractions.
Well, that should be about the same as -5/9.
Okay.
About half.
Okay. What is next? Delta U, delta R. Negative.
Positive. So
I was feeling it should be negative. Where did we miss it?
Delta U over delta R.
Mm-hmm.
Oh,
Anything negative.
Delta U is negative. Delta R is positive. No? So it is 1/9, but with negative sign. What is right? What is wrong? This is right on the board.
Board is right.
Okay, then we need to continue what is on the board.
So because the delta U is negative, the delta R is positive, and then there's a minus sign. So it's positive.
But it shouldn't be.
Why?
no, it should.
What is this? Is it U or delta U?
That's delta.
Delta U.
Okay, yeah, so delta. And it is
Not have a
it
positive
is
one, right?
it is positive.
No,
But we don't want
the
that.
second.
Oh, okay. I think we are surviving. We are floating up. We are not sinking. The sign here was negative, 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 and now we are getting positive.
Yeah.
Okay. So probably algorithm is not perfect, but it at least can help in the simplest way.
But if you think about momentum, it takes time for momentum to reverse, so that might be why.
Okay. Now we do this plus 13 over 81. There should be some simple decimal like 0.15 approximately.
You could say 1/8.
Yeah. 0.15 would be easier to and divide by delta R, which was 1/8. Not so bad, we can cancel 8 when we still in the natural fractions. So T stays here. 13/9. And now we do have a negative sign. So it was plus here, plus here, plus there, and then finally we get negative. 13/9, no objections? Okay, square root of 2, 1, 1/3 from gamma, minus 13/9 from gradient, and 1 from delta t.
So that's about 1/2.
So negative, how many?
13/27,
13/27,
which is
which is very close to 0.5. So this one was our previous coordinate, 7/9, and now we do 7/9 minus
You,
13 over 20.
if you kept the 27, you could times both top and bottom by 23, and then
By
you
three?
get 21 minus
Yes.
13 over 9.
Minus 13 divided by 27. Right?
Yeah.
It is what Levi suggested and no one objects. B 8 over 27. And 8 over 27 is about 0.3, a little more. The energy. No. Let's assume that it is 1/3. So the energy is 1/9. And delta U
So
will
then,
be
Overnight.
13 minus 9 over 81. 4 divided by 81.
no, wouldn't it be 49?
Huh?
Wouldn't it be 49
No.
minus?
Yeah. P times 1/9 by 9.
No, 49 minus
49
9,
minus
not
Wait,
13.
Yeah.
The 13 was the
Because-
delta U.
Yeah.
Wait.
So it should be 49 minus 9. Actually,
I do not see 49.
Right here. So we did
Oh yeah.
this step by taking 49 minus 36, which came from here.
Oh, it was delta.
So
In our previous
49
value.
over-
So it was previous value.
yeah.
Yeah.
Okay, yes, now I see.
So 49
49 minus 9.
which is about half.
We're doing
So about 40 over 81, yes. So about 0.5. So our delta U was minus 9, minus 15, minus a little more than half, and it is half.
we have to flip those numbers. It should be 9 minus 49.
Okay, minus. If you, I mean,
Yes.
It'll be
so negative 0.5, negative half.
Good.
Ah. You don't want to go further. Let's set up our tolerance limit
Big 25.
to be 0.52. Now we are, delta U is smaller than epsilon, and we claim success. So equilibrium position of harmonic oscillator is 1.3, according to this algorithm, which is not terribly far from 0. Does it work?
Yeah.
More or less?
Less
Do
than
I ever
a
want to do that ever again?
fractions or something.
Try it once again with different delta t as a homework.
If we write a program for it, would it be fine? Or do you have to do it manually?
Just give a table.
Oh,
I
okay.
don't care how you
That
how you
works.
feel.
Yeah. Then you can do it by
The flip side is extra credit, but I think it is too much. So I wouldn't do it. Just do the front page.
And this is due when?
Tuesday, so that you have a pleasant weekend.
So how many more
Do not torture yourself more than necessary. Just see if it converges or diverges. Just see some general trends.
do you have to submit the 2 problems or
No. Do
No.
just one. Extra credit is like if you plan to finish here and not come to the course and you already want a grade.
I think, how do I do it? Camera control. Okay, by now we have achieved success in finding equilibrium position of harmonic oscillator, which according to our algorithm is 1.3. We got an idea how the optimization algorithm is working, and as we go forward in the course, in the next couple of meetings, we will try to make computers to do it instead of us for real systems. With this, I thank you for your time spent in the course and announce completion of the lecture number 7. Meeting is dismissed. I will stay here in case some of you have questions.
Maybe we should